Welcome back. We're here. It's a beautiful day in Iowa. It's great to be alive. A couple things I wanted to start class with. You saw a note on Monday about the final. I didn't want to get everybody upset. But I have this new thing where I'm doing the oral final, right? The verbal, I hate that word for exams. Oh, the oral defense, all that stuff. No. Anyway, I'm doing that. It's a final. Final's a conversation with you and me, right? It's 10 minutes, and I'm going to present with you, each of you, with a scenario about like a real-world testing, whatever, and I want you to use what you learned in class to talk about that. Again, it's only 10 minutes, so it's not going to be very long. I'm not going to be like, what, on page 31 of this one article, but I would ask you to read the stuff that I've assigned, because that stuff may come up. I'll be like, oh, where did you get that? Well, in this article it said this, or this article it said that. That's what I'm looking for. I hope this is an understandable rubric of what to expect. I have it in the announcements, where your points come from. I don't want you to worry about this exam. I'm not here to, I'm not going to ask you, like, what's the Cholesky do? Or,
I love Cholesky.
I mean, who doesn't, right? I hope by now everybody loves Cholesky. But I'm not going to be asking like, here's an IRT model, integrate out theta for me or something like that, right? Or better yet, go and estimate this model in 10 minutes. It's not going to be that, right? It's more about the big picture. So I wanted to find a way to fit a 10-minute conversation into it. So my idea was I'm going to come up again with some real-world scenario. Not everybody's will be the same, okay? I may have a whole handful of them. There may be 5 or 6. There may be more. So if you look on the MyUI website, it gives us a final exam day of Tuesday. But since we're in a non-university classroom, I'm just going to make it our normal class day of finals week. But it'll be in my office, right? And there's a sign-up sheet right here. You can click the link. Many of you have already signed. Oh, you guys are so awesome. Thank you for signing up. You just have to be in my office at that time. I put a little bit of a break in between each of them, as you can see. So you don't have to be here the whole time. You could use this room as a waiting room if you wanted to. You just come at the time that you need to have it. That's all, okay? I'm hoping this will help alleviate the mystery of it. I'm also hoping that the final, in a way, I want you to prepare for it. I want you to not just walk in cold. So I'm hoping that what it achieves is that you get that last bit of, look, I know many of you do work, all of you work hard. I know that, and it's hard to fit all this in the class. When I was in your shoes, the thing that always fell out was the reading. I don't know about you. Now, I'm not accusing anybody of this. I'm not going to complain about this. But I'm hoping you do spend a little bit of time with the readings before this. That's the goal of the final, right? To give you a little bit of a reinforcement for it. And on that note, you have a homework due next week. I think there'll only be one more homework this year, all right? Now, it may be a longer one. It may actually be due before finals week. Like I might assign it next week and give you almost a month to work on it. Envisioning 2 different types of problems that are based on next week. One's a latent variable interaction. One's a higher order model. Both of those are within your skill set. But basically, to understand your workload, I will try to reduce how many things you have to do for class so that you can perhaps go back and try to read those readings a little bit. Because those, I find I tried to pick readings carefully because I felt like I didn't want to overwhelm you. There's so much to be able to read, but some of these are really foundational readings for what we do. Okay? Okay. Question.
Will there be any analysis sort of thing?
No, it won't be, here's a number interpreted.
It's more going to be like, this is what I would do, or this
That's
is why.
This is how I would build this, or how I would hypothetically analyze these data would be this type of model or this type.
Preliminary sort of.
That's right. I'd be like, here's a scenario. Many of you who know me, my life right now is dealing with a data problem. I'm not going to go into it in depth right now, but just know that I'm dealing with a lot. It may be borrowed from that data problem to see how you look at it as well too. All right. So I don't know exactly, but I'm not trying to pull a trick on you. It'll be one of the types of scenarios that we would have talked about in this class already. Like we talked about assessing standards unidimensionally, multidimensionally understanding how many, creating assessment, not knowing how many dimensions are in it, creating assessment that's built to be unidimensional. What do you do? These are the types of scenarios that you see. And each week there's a different type of scenario that motivates what we're doing a little bit, even though I lose sight of that, and this is one fault of my own when looking at my own lectures. I may sometimes lose the forest from the trees. I may sometimes focus on the details of trying to get the analysis done, because those can be really difficult from the why am I doing it, but the why we're doing it and what happens is really what I'm thinking of. Does that help? Any other questions? I shouldn't just be cool. No. Other thoughts or questions?
Can we have a potluck while we're waiting? Like in this room?
Yeah.
That's a really cool idea.
I think that's a great idea.
It might lessen the stress too.
Yeah. Why not? Why not? You want to do that?
I really like that idea.
Could I volunteer? So you're not even enrolled in the class, so it's not like you're not even going to take the final. But
I need the support. I'll sit here.
But Nathan, since you offered it, would you organize it?
I could, yeah. The Discord.
I mean, I'm not involved. Let me know what I need to bring. It has to be allowable on campus. That's the only rule. All right, okay. We're not doing the final off campus. We're going to keep this by the book, and I need to keep my job. Okay? So, something that's, tell me what you want me to bring. It'll be fine. That type of stuff. But
well, is there like a fund for, like, because I know there was pizza for the Bays thing.
Yeah, that was my pocketbook.
Oh, was it?
That was my wallet. But I can do that.
Well, I don't want to.
I just need an easy button. Tell me what you want, and I'll try to arrange it. Okay. And if it's ideally somebody could pay for this, let me know. And if it's, hey, we'll bring some snacks of our own, do that too. Just let me know, okay? But I'll let you all organize that, because my life's a mess. So.
Yeah.
I mean, not in a bad way. It's fine.
Whose is it?
Yeah.
Telling you. I don't know. Is it me being old is the problem? Anyway. Current climate. But let's not let that climate affect us. Mm-hmm. And if I'm part of that climate problem, you let me know, because I can fix that. But I don't know. Does everybody feel that way right now? How's the semester going for everybody?
I look forward to EMS stuff. So.
EMS stuff, yeah. That's
Or
good.
just like stats in general. Like stress comes from other places sometimes.
Gotcha.
I look forward to Thanksgiving.
Thanksgiving will be good. The break will be good, certainly. Sleeping is good too. Well, on that note, let's talk about the past. You all turned in a homework last week. I looked through all of your results and I gave the thumbs up. Everybody's doing well. I don't give you the micromanaging. I read, though, the last part of everybody's, and I found it fascinating.
Sorry.
Why are you laughing? Maybe that's not the right word.
Fascinating, which means it was very diverse.
Well, think of it this way. This was sort of an experiment, right? All of your data sets are real. They may be permutations of a real data set, like they're bootstrapped samples of the real data. But that's a lot of the signal that's in the data that really exists there. And the variance of what you found was incredible, right? But there was a consistent pattern. And I found it to be almost uniform, not with the exception of maybe one or two of you. How many of you, when you ran the PCA analysis, principal components, found a different result than what you did with the likelihood ratio tests? No. Now, some of you were using the standard of eigenvalues over 1. Some of you used the standard of scree plot, sort of where the bend of it was. Now, those are different, but many of your data sets had a different result if you looked at a different method you had. So think about what that means, right? If you're sitting here and you're like, how many dimensions do I have? The answer to that question is going to be very different whether you use a principal components or whether you use a likelihood ratio test. That makes me nervous. Does it make you nervous? What's the right answer? Or the flip of it, what can be used in good ways versus bad, right? Right? If you want this to be unidimensional assessment, there's probably evidence to suggest it's unidimensional. If if you want it to be multidimensional, there's probably evidence to suggest it's multidimensional. I mean, everybody here, I believe, with the exception of maybe one of you, found multiple dimensions. How many of you found multiple dimensions? Let me ask that in your homework.
They're very highly correlated.
That's going to happen. How many of you found a single dimension? Maybe. Right? Yeah.
Well, I made the argument that if you wanted multiple dimensions based on all of the stuff I was finding, you could argue up to like 10 dimensions, but the unidimensional model still fit just fine.
So what do?
I just went the unidimensional model because it's the simplest model that's most interpretable.
So that's a great statistical analogy, but what if your contract was for multiple dimensions?
Well, since I could make the argument for up to like 10 or 12, which however many they wanted.
There we go. The point I'm trying to make is we rely on a lot of these statistics to tell us what we need, and you hear people saying there has to be 2 or there has to be 3 or there has to be 4 dimensions or whatever. Or how do you know there's 4 dimensions? That's what I hear. You don't have multidimensional data. It's like, well, really there's sort of ways that you could claim each. I mean, in the absence of really like the limit, right? Where if you have literally the same theta in 2 dimensions, the correlation of 1, your estimation isn't going to work, right? It's just going to break. But how do you make that claim? So I found that fascinating in a number of ways. Think of the ramifications of what that means, though, right? I sit here and I tell you my perspective is multidimensionality is a good thing. We should be taking as much information from tests and using it to our benefit. I like that strategy. People resonate with that. It seems like it runs a home. The counter is always, but how do you know there's that many dimensions? Now guess what would happen, right? I've got me saying there's 4 dimensions. I've got somebody like a reviewer or who knows whom saying, no, there's only 1. Who's right?
Well, it's all a little bit subjective, isn't it?
It is, and that's the hard part. And that's where we get back to that article we read that was not even published yet, the preprint that talked about the argument for use. I want to tie that back to it as well. Like what are you going to use the scores for makes a big difference as well too. So I come back to that as well. Like if you're building a multidimensional assessment because you need those multiple scores, right? There's always a way that you can find that. Like, and actually overfitting the data is not as bad, perhaps, because the worst you'll get is 2 of the scores will look almost identical, right? They'll be perfectly correlated. That's the worst. Right? And if they're almost identical, you kind of behave the same on each. But I don't know. What did you think of the assignment overall? What did you learn from it? Anything? That you don't want to be an operational psychometrician?
Well, for me, the more dimensions I added, the more NANs I got for standard errors.
Mhm.
So I wanted to investigate that more, so I was a little frustrated that I couldn't.
Yeah. There was a lot of people. There were several people who emailed me with that.
But that is why I ended up picking the more dimensional, because the NANs were consistently more and more each time.
Mm-hmm.
But it was a good homework in the fact that it was real data, and you can see what exactly happens in the real world and how you can problem solve that.
Yeah.
Are the NAs have them because it's approaching the asymptote? It's like dividing by 0 issue?
Potentially. It's unclear. You have to really dive into the technical aspect of the algorithm to know exactly what's happening. If you look at the MERT package, by the way, there's a number of different standard error estimation methods. There's a number of different methods out there in the world in general. So it's hard to determine it, where that comes from. But yeah, I think you make a good point. Here's the funny thing about the NAs for standard errors for the item parameters, right? The loadings. In this exercise, were we using any of the loadings for anything? We didn't. We didn't interpret those, right? So what the purpose of fitting a model was less the items themselves, right? Those were unrotated solutions. We would never really consider them, I don't think. The purpose was the point estimate of the log likelihood. And with that, you can do a likelihood ratio test. So in some ways, like yes, it's concerning that those standard errors aren't there. I don't know what the answer why that is. That'd make me feel batty also. And I think your intuition is right. But some ways also they're sort of, so long as we get a point estimate of a likelihood, we can do a likelihood ratio test with it.
Well, because you can do it doesn't necessarily mean that you should.
Right, but what does like a three-dimensional solution look like mean anyway in that case? That's the hell out of me, right? I don't know. So, this. What else? Let's see here. So how many of you had estimation issues in this homework? Like NAs, NANs for standard errors, models not converging? Yeah? If I had asked you to do this with marginal maximum likelihood, EM, not Metropolis, Hastings, Robbins, Monroe, which is like EM, but the E step is replaced with a Bayesian sampler, it would be way worse, right? You'd still be analyzing these data. That's the hard part for it. Had I asked you to do this with Bayesian methods, like we learned about last year, Nathan smiles. Nathan, tell them what would they get? And now you're worried about what you're going to say.
Hours long of waiting for it to sample, because when you add covariance matrices, that just needs to get.
It can. I will say Bayesian will give you a bit better diagnostics as to why it's not converging. And it's possible with the straight LKJ prior. By the way, the episode with my podcast, I was on a podcast talking about LKJs. Anyway, go to my website. You can find it here. I thought this is funny. Who wants to hear from me anyway? But anyway, that prior works really well, nicely, but sometimes it still doesn't work. So anyway, I got a podcast. You can listen to it right there. Learning Bayesian. Hear me talk to some guy from around the world. Anyway, long story short, I like the Bayes method better because if you get it to converge, you can always find standard errors. It's your posterior standard deviation, right? Always do that. Totally cool. But getting it to work is also hard, right? So are you coming away, well, I'm hoping what you're coming away with is it's not easy to do multidimensional analysis at all, right? We haven't even fit like the 4-dimensional IRT model yet. You've done unidimensional, you've done a couple of dimensions that were exploratory. We haven't done the confirmatory model yet in homework. At least I'm not aware that we have. Have I missed it? I don't think I have. Maybe we have. Anyway, I'm going to look back through the assignments. I need to prep for the final too. Long story short, one of the questions I asked at the beginning of class, if multidimensional measurement models are important and we all think that we should get more information from the test, where are they? I think you're running into one of the answers, right? Really hard to do. Really hard to estimate. And imagine that you're on a time schedule where you have to provide those scores like that. Right? It's really hard to do. But that is where, if something is hard to do, that's where a growth opportunity, who told me growth opportunity today? Actually, that was someone else. It's where your growth mindset is. You could really fit in, and like that's a chance where you could do interesting work to make it easier for people to run. So, any other thoughts on that homework? Anybody want to talk about what they found, what they thought about it? You want to yell at me for making you do so much? How's the next assignment going? I shouldn't talk about it? Let's see. Anybody want to talk about the homework that's out right now?
Well, actually, can I ask?
Yeah.
Was there supposed to be a formative assessment?
There should have been.
last week?
It didn't happen?
Well, so I logged in at like 8 p.m. last night, and I didn't see a formative assessment 9, but I saw 10, and so I did 10, but then I went back and looked at the questions, and that was actually about this week's lecture.
Okay. I'm just out of my mind. I swear I created one and it's not there. So, yeah. Don't worry about it.
Okay.
Completely. That's what I'm telling you. My life's a mess. You know, so under the influence of some really powerful antibiotics. So I was on drugs last week. But no, I'm sorry.
No. I just, it was 8 p.m. and I was like, I totally forgot to do this, and I'm logging.
And I totally forgot to do it too, and I learned about it at nearly 1 o'clock on the day it was
Yeah,
supposed to be due.
exactly. I just want to make sure I didn't.
Not here. Not here. All right. Anybody want to talk about the homework that's currently out while we have a moment? Vladimir?
Yes, I have one question because the last question says that we should give you the name of that model of that thing and the notation. What do you mean by notation? Like what the model is doing?
Yeah, what's the item response function?
Oh, okay.
Ideally put into the mixture framework that I gave you, that general finite mixture model
Yep.
equation where you've got and actually I'll go a step further, marginalize across the mixture portion of it. But if there's maybe other portions too, but don't marginalize across the others. You can, but I'll be lenient. But just try to convert M plus to notation. The hard part with M plus, that doesn't look like anything like a statistical model, right? You got percent signs, you've got brackets. At some point we need to go to an international keyboard to start creating new parameters, like because the characters don't look the same, right? So my goal in asking this question was to sort of tie model to M plus in a formative way more than anything, and not a punitive. I know I grade you on it, but it's a small part of the grade. So,
Yes, thank you.
you're welcome. Ahmed.
So for comparing models based on AIC and BIC, what if AIC behaves differently than BIC?
Is expect it
Okay.
and write about it. AIC says this, BIC says that.
Yeah.
And you know what reviewer number 2 will want? Something completely different from AIC and BIC.
Adjusted BIC.
Yeah, well, there's M plus gives you 3, but there's like a whole menu of all of them, right? This has been an active area of research for many years now, so good luck with that. All right, other questions on the homework? Yay, mixtures. So I rearranged, any other questions overall? Questions on life? I'm not the guy to ask for those. Let's see here. I seem very down today. I'm not really down. Actually in a great mood. I'm finally able to move a little bit and get back to life. So today I moved around the order of topics from where I planned because I wanted to cover DCMs, diagnostic classification models today. That is not what I need. Sorry, it throws off my whole screen if I do that. So what I instead need to do is, I haven't used, there we go. I know this looks a little weird, but that works a little better. So diagnostic classification models is today's lecture. Why DCMs? They are a multidimensional measurement model. It's where I got into most of my multidimensional stuff from. And it shows up today because they are, bless you, a finite mixture model as well. So this is going to reinforce the topics we talked about last time with the diagnostic model. Okay? All right. So I'm diving into the measurement models of diagnostic classification models. But I want to start with some non-slides here. Yes, I am reusing slides from previous lecture. I've been giving lectures about this model since 2007, so forgive me. They're still relevant, I think. But here's the big question. Why do DCMs exist is the question I have. What do they do? Why would you pick one? And the answer to that, I don't know that you would know that, but I don't know that many people would know that. But here's some history to it, right? In my life, my personal history, I started working with Bill Stout and Jeff Douglas and a bunch of people at Illinois around the end of 2001 on diagnostic models. And I didn't know it. They were called cognitive diagnosis models. They still go by the word cognitive diagnosis. I'll mention a little bit more about why I don't use that in just a bit. But the thought was, let's get more information from assessments. Let's do that. But this whole class has been about getting more information from assessments. So why would a DCM exist when a MERT model could do the same type of work is the question. And the answer to that is what you're discovering so far, at least my conjecture as to why that answer is. It's hard. like, why does research start? Why, a few papers start on one path and people pick it up and it becomes a field? Why is that the case in science? Who knows, right? There's a lot of explanations for why that was. But at the time where I was working on this, my mentor, Bill Stout and Jeff Douglas, were talking about this as a way that we could get more feedback to students who take these assessments. Well, isn't that like what we did with the MERT model? If we have a confirmatory MERT model and we have 4 dimensions and we give 4 thetas, that's 4 pieces of information, right? It's like a math test and we did standard scores versus the whole domain itself or subject math. 1 versus 4, that's more, right? But DCMs came about to do the same thing. And the answer to why, at least that I'm going to conjecture to you, or at least posit to you, is the difficulty you had in estimating your models, right? The history of diagnostic models or cognitive diagnosis, they became very popular in the early 2000s, and they exploded after that in the 2010s and so forth, I feel like. There were trickles of ideas of it in the 90s, and a paper there in the 80s or 70s, right? So there's this little bit of a history to it. Not to mention the work of the Tatsuokas in the 80s as well, rule space and model adjacent methods, rule space, knowledge, knowledge spaces. My goodness, I'm blanking on the name, Falmanier's work. Knowledge space theory. So there's all these systems that are out there. Why did they come about? Well, remember in that time, like today, not that time, today, we just decided doing multidimensional assessment's hard, right? Estimation-wise. Like the algorithm that you used for the last homework didn't exist until 2010, at least. And even then it was spotty. It wasn't as refined as this. So it's 2023, I think, last I checked. It's Wednesday, right? Anyway, and it's hard. Imagine what it would have been like in 1999 or 2001 or 1989, right? The demand was still there. The need was still there. But how you go about doing it was much harder. I'll give you another, go ahead.
When did the idea of multidimensional come about?
Oh, it's been with us from the beginning. I mean, you look at classical test theory, the subscores idea,
Okay.
right? And then multidimensional IRT, well, before there was multidimensional IRT, there was multidimensional factor analysis, right?
So were people trying to do this by hand?
Oh, yeah. I would say the first multidimensional psychometric methods were exploratory factor analysis in the 30s, or 20s and 30s. And that was all by hand. In fact, as I understand it, how many of you are research assistants right now? Like your job would be the computer. You wouldn't be using the computer. You were literally the computer, right? You were doing the math by hand to do that. And yes, analyses would take a year. What's that?
That sounds kind of fun. And she's like, no, thank you. I'm good.
So yeah, computation got better. I would argue the first multidimensional methods were the exploratory factor analysis methods that use principal components as a base. And then when you get into maximum likelihood, you start to see MERT show up again. But again, in the factor analysis world, it was much more developed because in psychology, it was really where I'm familiar with it driving that process, traits were looked at as having multiple dimensions. There's multiple sides of personality. And so therefore methodology sort of mirrored that. Whereas education, it was just a test score. So it didn't happen, right? There was another part. You'd say, okay, wait, limited information seemed to work really quickly, right? Remember the limited information methods you've been working on? Yes. However, limited information is great for picking up structure. There's one catch to limited information that's really difficult. How do you go about getting factor scores? Right? Because you don't have a full likelihood function. Are they limited information-based factor scores? Are they EAP factor scores? It turns out it varies widely. Like if you use M plus limited information with a factor score, you get MAP estimates of factor scores, maximum a posteriori. But if you use full information of anything, you get EAP estimates. Why do they differ? People have that problem as well too. So historically, when DCM started to come about as a field, it literally was, come on already, we need to get more than one score out of an assessment. How do we do it? And that's how I believe, at least my perspective, things had come about. So in many ways, they're redundant with what you're trying to learn in this class. But in several small key ways, they expand what we know about psychometric models. And that's where the fun part of this is. Because I feel like in my research arc, was heavy into DCMs. Now I'm not as heavy into those. I have my own reasons, which we'll talk about at a different time. But I learned a lot about psychometrics with DCMs that we don't see with MERT still, that we could still bring back to MERT as well too. So if you start looking at it that way. All right, how am I doing with the why? Okay, now there's another why. And again, I don't know that I'm going to teach a full class on this again. I might, but the other part of it is in a multidimensional IRT model, with every assessment that you have, there's only so much time you can assess somebody before they give you garbage results or just walk out, right? And this applies to the kids like my son in 3rd grade right now, or it applies to grown-ups who have to do, experiments where there's 200 items or something like that. God, right? It's just terrible, right? So when you run a multidimensional IRT model, if you think of an assessment, think of a string of binary digits, right? I'm going to sort of go information systems here, information processes, right? How much information is actually in that string of binary digits, right? There's not a lot. Like every item gives you a 1 or a 0, and you have a collection of those. And now you're going to turn that into not only a score, but a standard error as well, right? It's really hard to do that. So what usually happens in multidimensional assessments, those scores, you can't assess each dimension a long time, right? You can't have 100 items per dimension because the people are going to quit giving you data that makes sense, or they're just going to stop your assessment altogether. There's no time for it. So what happens to the scores if your assessment is short? How many items per dimension per standard? You have about 5, right? Most of you? Yeah. What do you think, how accurate are those scores with five items?
Maybe enough, just enough.
I think they're terrible. I don't even know if they're anywhere close to enough. But are they enough to give you enough information to do something is the question, right? And that something to me, if you're on that level, at least with the data you have, is help a student learn better in that semester or that curriculum they're in. That may be the case. Well, it comes to come to find out, if you compare a classification model with a scaling model, there's some very big differences, but there's some very big similarities as well. And it turns out the big difference is that in the classification model, it's a whole lot easier to put a person, let's imagine we have this underlying continuum. Let me see if I can do this here. I need my drawer, this one. And I want, yeah, there it is. There's my drawer. All right, so imagine we have a continuum here, right? Let's just call this theta, right? And what a DCM actually does is basically takes the theta continuum and cuts it. And over here, we call these sometimes masters. That's not a good idea. Sometimes we call these non-masters, right? Well, it turns out it's a whole lot easier to locate if a person's above or below a cut statistically than it is to pinpoint exactly where each person's theta might be. So what I mean by that is if a person is on, we just need to know if let's imagine we have a theta hat here and the interval may look like this. It's a really wide interval. We'd say relative to this cut, this person is solidly in this group right here, the higher performing group, right? Whereas if we have a person here, this is another theta hat, they might be somewhere like this. They're definitely in the lower performing group. And if this cut has any relevance to us, when it comes to education or learning a standard or so forth, this might be enough information to work. Turns out, when you look at providing a score that's not theta on the continuum, but the probability a person's above or below this cut point, right? That probability is a whole lot easier to achieve high reliability for. Right? That classification is a lot easier. It's a lot easier to classify someone than it is to put them on a scale. And so because of that, with 5 items or with slightly more than 5, maybe 6, 7, 8 items, we can get almost perfect test-retest reliability for classification for somebody. Whereas a single theta on that continuum would have so much error we wouldn't know what to do with it potentially. So the two reasons why DCMs existed as a field and still potentially exist as a field, one was they want more information from a test. The counter to that's always, but MERT exists, so do subscores. True. The second was, when I give a score, can I give a score that at least is useful and somewhat accurate? Useful meaning, hey, you're in the high-performing group. Accurate meaning you're consistently in that group. There's a really high chance that happens. That's the goal, right? So it's a different way of looking at data altogether, but it really is how DCMs function. Any questions on what I just said? Weird way of looking at it. Yeah, I was lucky, really lucky to be part of that lab. I hope I've underscored that point. Gratitude, absolute gratitude. So I was a pain in the ass when I was in it, because I'm a pain in the ass always. You know that about me. But, so I'm saying this now so that if anybody from my mentors listen to this, because will be on YouTube, gratitude, okay? It's all gratitude, even if I'm frustrating to work with. The problem I always had there was why? Why are we doing this? Why can't we do something else? And that's a scientific question. That's a good question to ask. But I do think DCMs are such a widely written about topic, we should talk about it at least a little bit. So, all right. So we're going to talk a little bit about the models. I'm going to talk about one single measurement model here, but it actually is more than one. In the history of writing about DCMs, there were a whole bunch of these models, and then there was a unifying model that showed up. This is the unifying model. Just sort of put them all together. And they'll go from there. Sergio, you probably give this lecture. Sergio learned DCMs at Georgia, right?
Primarily, yes.
Primarily, so yeah.
So diagnostic models, the latent variable is assumed linearly distributed.
That's it.
right?
That's it.
So-
We're gonna get there in just a moment. Yeah.
Okay, I have a question about that when we get there.
Yeah,
About
yeah.
something else.
Yeah. Once I show the model, I'm then going to show it what it's like compared to IRT. It will not be in these slides. I'll write it down.
Okay.
But literally, think of it this way. If I said the word multivariate Bernoulli to you, what does that mean? Where have you heard that?
Basis classes. We went over it yesterday a little bit.
I had it here. Come on.
that
Don't
too,
get,
yeah.
don't give me this Lisa stuff. What is the basis for a limited information model fit? Multivariate Bernoulli. Sorry. Bring Lisa in here. Give me a break. Sorry, I'm just kidding. I hope this is a joke.
Yeah.
This is a joke. Nathan, I don't want to embarrass you.
No.
It's just-
We'll go on and.
I'm always having to care for it. It's Lisa, Lisa, Lisa. I always hear it.
Well,
I'm just
now
kidding.
we have that on YouTube.
I know. No, I'm absolutely going down the list here. You've just touched on it. Oh, well, Lisa covered it. Oh my God, of course she did. Yes, I know, and God gave her slides, right? I understand. They're great. Sorry. Boy,
They've got like a goal.
where's the psychologist that I need today? No, I'm just kidding. Lisa does talk about them. They are important. That is, I apologize. I'm making a joke of it. And the multivariate Bernoulli is the basis. Where I first read about it was the Madeo, Oliveras, and Joe paper with the very first limited information that defined it. And if you remember the limited information model fit, where you had that paper to read that became impenetrable after a while, right? That one, that's where multivariate Bernoulli shows up. So here, this way. If you have an IRT model, what's your a MERT model? Let's say you have 4 dimensions. What's your distribution you assume for theta, usually? What? Multivariate normal, yes. 4-dimensional multivariate normal. If I flip that distribution from 4-dimensional multivariate normal to a 4-dimensional multivariate Bernoulli, I have a DCM, mostly. That's it. There's an additional component, which is DCMs started with latent variable interactions. So if you have an item that measures more than one latent variable, almost by default, DCMs estimate latent variable interactions. But the bigger picture, when you talk about this, we're doing psychometrics with multivariate Bernoulli assumptions of the latent variables. Now, does that make it feel weird? Nobody ever thought about that, right? But here, if you're talking to somebody in a different audience, let me give you some tips. What do DCMs do? They're mixed models, by the way. What we're doing is mixed model. Mixed effects models, random effects. Latent variables are kind of like random effects. But don't always assume the random effects are Gaussian. When you say that in the stat department, people go, oh, well, why do you do that? Let me ask, that's different. What are you doing? We're doing psychometric models with discrete latent variables. That's the thought. And actually, last week, even though we didn't phrase it that way, the latent class model was that way too. Our assumption of the latent variable was multinomial, right? Whereas the set of categories, they were not ordered. There was nothing else to it. It was like a nominal level of measurement, but it was a multinomial. So now what we're doing is we're changing up the distribution of the latent variable from a technical point of view. So that's there. I just said it. You have a question?
Well, when we get to the
model?
Yeah.
Okay.
Yep. I'm wondering, can theta be to follow any distribution?
Yes.
Okay.
Yes, that's the point I'm going to make.
Yeah.
So if you think of it this way, what does generalized linear models that class tell you? Sorry, what does linear models tell you? I guess we do it intermediate here.
Residuals are normally distributed.
We're going to predict data. The data are continuous. We use a normal distribution for the residuals, yeah? And generalized told you, oh, I don't have continuous data. I'm going to pick a different distribution of my data, right? In a random effects sense, almost always the random effects are normal. But there is actually another class of models. I don't think that people wrote about it much or still write about it much, but there was a set of papers in the early 2010s that talked about doubly generalized, where the random effects were also no longer normal as well. And this is what's happening in psychometrics with what we're doing here. The data type can be any distribution. The model type can be anything. The latent variable can be anything. Bayesian networks sometimes get thrown around like that because you have a set of collection of variables with distributions, whether they're random or latent or observed. So I hope that answers your question.
Mm-hmm. It does.
Am I going too far? Anybody else want to ask any questions? Excuse me for moisturizing. Got a Kleenex box, got some Blistex. It's all good. All right, so let's talk about where these models came developed. In 20 plus years, a ton of these DCMs have been developed. We're going to look at a set of models today that are latent variable based. There are a series of models that are similar to this that are not latent variable based. So again, this is a measurement model, very much like we've talked about in this course. One that we're talking about today is something called the log linear cognitive diagnosis model. You see the word cognitive diagnosis there. Bob Henson's the lead author on that. I was co-author on it. And right around that time, I'm thinking about it like literally, if the only difference in these models is I can switch the distribution of my latent variable, why don't we, two things. Why don't we call it cognitive item response theory, right? And number two, what does cognitive mean anyway, right? Sometimes we use the word cognitive to imply aptitude tests, right? Sometimes we use it to imply cognition like in the brain. I came from a psych department. Cognitive is much more lower level than what we're doing. But beyond that, I call them diagnostic classification models because cognitive is really the application in a very specific area, cognitive assessments. But we never name any of our models with the application in mind. Very seldom do we do that. So we want to generalize. A diagnostic classification model fits with any type of data. A cognitive diagnosis model better be cognition, right? The first paper I ever got published was using cognitive diagnosis models. I think it was called the use of cognitive diagnosis models to assess pathological gambling. Okay, cognitive and gambling. Those are not used in the same sentence, right? Those aren't the same things. But I use the type of methodology. So I call them diagnostic classification models because it separates the methodology from where it's being used. And I wanted these to be more broadly used or thought of as methodological tools, a methodologist that I think of myself as. So that's why I call it diagnostic classification model. But at the time we wrote this paper, we were still calling it cognitive diagnosis. The other thing that you get when you call it cognitive diagnosis, by the way, is that people think you're getting more information from the test because you developed it differently. And most of the time, none of the test development is different for what we're using these models for. Right? It's the same test that we would use an IRT model for. So there's nothing cognitive about it. It's just literally. So I found that to be somewhat overblown. But there are people who are like, yeah, we need cognition in the assessment. Yes, absolutely. There's a whole SIG in AERA. I helped co-found it with Joanna Gorin. Cognition in the assessment SIG, right? What does SIG stand for? Study interest group, something like that? Special interest group, right? So there's a bunch of people talking about cognition in the assessment. Heck, I have an old monograph on my bookshelf somewhere. I picked up the Burroughs Institute in Nebraska had a conference on cognition in assessment in 1984, right? So that's like really important. We make our tests do cognitive things. I'm not sure what those were, but anyway. So that's why I'm like, get the cognitive out of here. We're not doing anything cognitive. We're just switching out the latent variable. All right, enough. So each DCM that has been developed up to that point makes a very specific assumption about how you get latent variables to interact. Now in DCM world, the latent variables are called attributes. So you'll see the word attribute in these slides. Substitute that for latent variable. A couple weeks ago when we had those diagrams of the contour plots, you remember when we did a compensatory model where the latent variables were additive. The contour plots were lines, right? But then we got into non-compensatory models and they were curves, right? Basically, the DCM world struggled with that to begin with. Compensatory versus non-compensatory models, right? Those were the two distinctions. And so when you were creating a model or an assessment, not only would you have to create a Q matrix, which we all know is really difficult sometimes, depending on what you're assessing, you would then have to go and say, yeah, and I think the items that measure more than one thing, they are all non-compensatory, right? Or I think the items that measure more than one thing are compensatory. Well, that takes a difficult task and make it even harder. Who knows what that means, right? So that was where it was at. So back before the LCDM, you had to go, thankfully the field was small. The field is still small. So really nobody was doing anything with it back then. Now people are doing things with it, but it's still kind of there. Then in 2005 and then 2009, Matthias von Davier had the general diagnostic model. It tried to come up with a linear function for attributes. We expanded upon that, we being Bob Henson, myself, and John Wilsey, created the log linear cognitive diagnosis model. Bob had this idea. But the difference between the two is that in the log linear cognitive diagnosis model, it sort of assumed the interactions being present and being at an item by item level. It's a small trivial difference from where the GDM is, but what we did was basically we try to acknowledge the GDM's notation, and we use their notational system to do that, to sort of extend it. And then there was something called the GDINA model that came out after the LCDM that's basically identical to the LCDM. So I only do LCDM. So the LCDM, we showed in the LCDM paper that each of the models that were being used at the time, the compensatory versus non-compensatory aspects of them, could be explained by the pattern of main effects and interactions in the LCDM. Meaning, no longer, once you build your Q matrix, did you have to say this item's compensatory, this item's non-compensatory. You literally could have the model and the data figure it out. So now you have an analysis model that works for all the time. It's a general model. It subsumes all the other DCMs, so if your data truly are non-compensatory, it'll be non-compensatory as a model. That's fine. I don't know who cares if they're non-compensatory or not. It doesn't really make a difference to me. But the other thing the LCDM did was take models that didn't look like our normal psychometric models. They were all expressed in probabilities, generally, and map them onto the logit scale where we can now do a quick evaluation and see where the differences lie between IRT and DCMs. So that's what this is. So I'm going to go back to the future. Some of this is really early stuff, but I'm going to keep us all on the same page. The other way you can think about it is, if we observed all the variables in a MERT model, just a compensatory MERT model, if they were observed, what would it be called for one item? Logistic regression, right? You've got binary or categorical item response, link function, linear predictor, additive MD-effects. It's logistic regression. The LCDM, logistic ANOVA. Literally is dummy coding latent variables, which is pretty cool. So if you know ANOVA, we're going to go heavy into ANOVA today. Cool? But we got to have logits, we have LCDM, and then we get into more general forms. So today the latent variable will be denoted with the letter A for attribute. And people will be respondents. If you read the book, I assigned one of the chapters for my book a long time ago. It's sort of the general chapter, but that's how we describe it. We wanted to be general enough so that people outside of just education would read it. I don't know that we achieved that goal, but respondent was a neutral enough term rather than person, examinee, subject, student. So respondent is who's giving us the data. The latent variables themselves we're going to denote with the letter alpha today, not theta, right? I know that sounds weird, but that's what happened in the DCM world. Everything was an alpha. Alpha A, A in the Greek alphabet, right? A for attribute, all synergistic, right? Anyway, turns out a person will have a profile of attributes. And each of these attributes today are going to be defined as either being a value of 0 or 1. A person with a value of 0 has less ability than a person who has a value of 1. But remember, this is a classification, right? That's like saying over here, alpha equals 1 up here and alpha equals 0 over here on this side, on each side of the cut, right? So you may be saying to yourself, you just gave them a theta. Yes, I did. Now that theta has no meaning on as a scale. It's a grouping variable. It's a dummy code or a reference coded variable. It's really raining outside. Anyway, I don't know why that popped in my head. It's raining. Of course it's raining. I'm talking DCMs. Where else would you want to be? Focus. So I don't care that this is a 0. The people in this group are not 1 unit better than that group. What we're going to come to find is within a group, we cannot make differences about people. We've classified them all to be the same. So a DCM, anybody who's in this high group up here are treated equivalently. They're all in the high group. Everybody in the low group are treated equivalently. They're all in the low group. But the one thing we will know and how we set up our model will enforce this is that the high group has more ability than the low group from an ability perspective. How much more, we don't know. But we know they have more. Okay? So what type of measure is that? If you know that being in the group describes a little bit of the quantity, but not how much more of the quantity, let me back up. What are the levels of measurement from basic stat? Ratio, something with a fixed 0, continuous scale, interval, fixed 0 point, ordinal, nominal. This is an ordinal measure. We have an ordinal latent variable here. When we give you a grouping, you know if your grouping's higher performing or lower performing. That's it. You don't know how much more. IRT, or multidimensional IRT, is interval, we'd like to think. And then latent class is actually nominal. So there you have it. And for those of you who really are interested, go and give yourself a Poisson latent variable and make it, ratio. I don't know. There's no way of doing that, but still. But that's it. That's what we're thinking. Okay? Okay. So these alphas today are all 0s and 1s. Right? So now we have a vector. If we're measuring, let's say, 4 attributes, there'll be 4 zeros or 4 numbers that are either 0 or 1 for each person. But because they're discrete, we actually know there's a finite set of them. Right? If each attribute can take 2 values, then the total number of permutations or attribute profiles a person might have is 2 to the number of attributes. Right? So if we have 4 attributes, there's 8 ways a person could have 0s and 1s. Right? From all 0s to all 1s. There's 8 permutations. You want me to write them down? 4, 16.
Yeah, that's why I was confused.
16. 8 if we have 3. I don't know why I say 3. Thank you. 16. 16 different ways. Right? Turns out each attribute profile is a latent class. Ha-ha! Now you see why I put this here. And here are the latent classes last week. All right? So if each attribute profile is a latent class, now we have a latent class model. But we got to do something to make sure that each class maintains the meaning of a profile itself. Because you saw last week, the latent class model has some problems with what we call label switching, where, you know, Nathan and I may run a two-class latent class model on the same data. My results under class 1 look identical to his results under class 2. It means the name is switched, but the meaning has not. If that name switches here, we're in big trouble because we put meaning onto these latent classes. Right? So that's part of the point of view that we have here. Okay. Any questions so far? Okay. So we have a number of items also. You're used to that. You're used to the Q matrix. Cool? All right. Let's talk about ANOVA. The LCDM is like an ANOVA model. I know you all know ANOVA, but I'm going to just refresh our memory. Because if you're like me, particularly as I get older, I forget a lot. All right? Anyway. The latent attributes are categorical, meaning that there's only a finite set of these possible mastery statuses, right? Any specific profile or permutation of the attributes are called a profile or a mastery status. So basically, for any attribute, we know that there's a 0 or 1, and that's going to predict the probability of a correct response. This is, the LCDM is very similar to ANOVA in that we're predicting a dependent variable, in this case our item response, as a function of what group a student is in, a respondent is in. I can call this experimental group if we want to. But that's where we get this design from. Analysis of variance with crossed factors would look like an experimental design, right? So let's talk about ANOVA real quick. What was it, the Hawthorne studies in the 1930s? They looked at, no, maybe that's not it. Anyway, there was famous stories with a huge confound in the 30s, but I think that was satisfaction, not job output. Anyway, let's imagine we're quantifying output of people working. I don't know what they're doing. They're building thetas. I don't know. What do you do in your job? They're writing R code. There we go. Writing stand code for you, Nathan. We got some stand code here, right? Sorry, not just you.
No, you're
Anybody else want to? I'm not picking on you. Anybody else want to be the stand person today?
I think I'm the only one who likes stand this much.
It's okay. I do too. All right, but let's imagine we are seeing how much you can write R code, and we want to vary the conditions you're working in. If this were Linguist Center, it might be number of rats, number of cockroaches, but it's not. It's the lighting, how well lit. I guess Linguist Center sometimes loses its lights, and how warm or cold it is. Oh, that's another Linguist Center thing too, right? So here, now we have, if we took people and randomly assigned them into a lighting condition and a temperature condition, now we have an experimental design, right? You've seen this before, right? It's a two-way ANOVA. And if we randomly assigned it to all 4 different conditions, all 4 permutations, that's a crossed two-way ANOVA, right? Like this. And you've got your ANOVA model on here, right? Now in the ANOVA model, what it helps us do is we can test for a main effect of temperature, like the first factor. We test for a main effect of lighting. We can test for an interaction of temperature and lighting as well with each of these effects. But we also could go and dummy code our variables a bit. And if we dummy code our variables, now the warm condition, this makes me think, oh, this is a warm respondent. It all should be sort of warm, right? I mean, sorry. Anyway, somebody who's in the, this respondent's high, all right? So I'm going down the road. I gotta leave that alone. Take a deep breath. Hold on a second. I need a drink of water after that. I'm gonna randomly assign people to body temperature and how intoxicated they are. Okay. Now that has an impact on how much code you write. I have to imagine. Is this taking it?
Not from experience.
No comment. No comment. But yeah, anyway, if somebody's in the warm condition, they get a 1, a 0 otherwise. If someone's in the high lighting condition, they get a 1, 0 otherwise. Right? And so now that ANOVA model you saw before just looks like a linear regression model. Each of these are dummy coded. Each of these effects have a meaning that we can describe, right? Anybody want to go through this pop quiz on linear models? No. Beta 0 is the mean of somebody who's not warm and not high, right? That is somebody who's in the low light, low temperature condition. That's their mean lines of code they wrote. Beta T, temperature, is now the difference in the mean for someone who's in the warm temperature condition and the low lighting condition, right? It's a conditional or simple main effect. That's the catch. Remember, when you have an interaction in the model, right here, each of your main effects are conditional on the value of the zero, the variable that is 0, the multiplying variable for it, right? It's conditional on where that 0 point is. Do you remember that? Drilling in. I know Lisa is great about interactions. And I know I just went out, Lisa, but Lisa's slides are great on interactions, right? Same thing with beta L. That's the difference in the mean for someone in the high lighting condition when they are in the low temperature condition, right? And then the two-way interaction is the over-additive or under-additive, the shift that occurs to it. And as you remember, particularly in multi-level models or anything else, that interaction will moderate or modify these main effects, right? So it could be the change in the difference or the difference in the change or something along those lines as you go forward. It still applies here as well. It's just seldom thought about in latent variables, but it does. And here, this is ANOVA, it's not even latent variables yet. How are we doing? Okay. ANOVA and LCDM take the modeling approach. We are going to predict an item response using a set of dummy-coded variables. Those dummy-coded variables are our latent variables in the LCDM. They're our thetas. They're zeros and ones. That's it. We are also going to build for each item a series of main effects and interactions. Now you'll note that's going to depend on the Q matrix. An item that measures one attribute or one latent variable only has one main effect, always. Right? It's only when you get to an item that measures more than one that you have to worry about this. And the same thing works in MERT, right? If you have an item that measures more than one theta, then you worry about the type of contours you have, whether they're linear or whether they're curved of some sort. And then, just like in ANOVA, we may look for ways to reduce the model, the complexity, right? So if we estimate a model and we see an interaction is not significant, oftentimes we take the interaction out of the model. Well, it doesn't really make a difference here. But there are some differences between LCDM and ANOVA. Number one, that example I did before with a continuous variable using a normal distribution. We've got binary variables. Today we're just keeping it with item responses being binary. Remember, you can have any type of distribution. In fact, there is an LCDM that uses continuous distribution, and that's like the factor analysis version of it, right? But today we're just going to work on the binary items, so we're going to deal with logits. Okay? The attributes are dummy codes. These are latent factors. We will say that a person has mastered an attribute if they have a 1 and not mastered they have a 0. I really actually have come to dislike that term. Like, what does it mean to master something? No idea. What does it mean from a statistical point of view? If this is a MERT model, oh, theta bigger than 3, are they masters? Theta bigger than 2? I have no idea. How do you decide that? Mastery is a very important term in education. We talk about mastering some content or some subject, but it doesn't map well precisely to the numbers because my definition of mastery and your definition of mastery might be something different. Just because somebody's in a high group from this perspective, just because somebody's on the right-hand side of this line in the middle, doesn't mean they're a master, it just means they're in a higher performing group. So I don't like the term mastery, although you see me write about it. If you read my papers, it talks about it that way. That's how the field does. But mastery is really, you need an additional level of validity evidence to suggest somebody who's called a 1 is really a master. I think right now it could just be a statistical artifact. Too much information I'm giving you right now. Finally, the LCDM is going to treat all latent variables as being crossed experimentally. Remember the idea of the crossed effects ANOVA? Meaning, in this 2x2 table, we've assigned people to all 4 cells, right? And by that crossing, we're able to estimate so long as we have more than one person per cell, an interaction in ANOVA. The same thing happens in the LCDM. We're going to treat all combinations as crossed and assumed to exist. Turns out, if you have things like a learning progression, an attribute hierarchy, things that you have to master ahead of time, that's not going to be true. They're not going to be crossed because, let's imagine this is master versus not, and master versus these are masters not, these are masters not. Like if you had to learn this, if you had to be a master of this before you were a master of that, you would observe nobody in that cell right there. These are people who are masters of the subsequent thing you had to learn from before. And you think of how we do things like in mathematics where we build upon what we're learning, it seems very plausible that that could be the case. Now it turns out estimating the LCDM, you may run into estimation difficulty in that case because there's 0 people there, but it doesn't hurt you as long as you can get estimates. It'll be valid, they just don't work. But just like in linear model land, we talked about crossed ANOVA, there are other versions of ANOVA, right? There are nested versions of ANOVA. Turns out when you have an attribute hierarchy, you can estimate a nested model ANOVA. That I did this a while ago. It was called the HDCM, the hierarchical diagnostic model. But basically it's just change your linear model, make it latent, and have it work. So not only are we changing the distribution of the latent variable, we're also changing sort of the modeling perspective as well too. But I'm scratching the surface of all of this right here. How are we doing? Questions? No. All right, you know about logits, but I'm going to tell you a little bit more, right? You know the logits. I give these slides to people who may not know logits as well. But here's why I wanted to tell you about logits. Because some of our model parameters in the LCDM give you values of logits that are weird, like -6, right? Or +12, usually when things break down. But if they're all logits, remember, 0 is the 50-50 probability. 0.9 is like 2.2. 0.1, the complement of 0.9 is actually -2.2, right? It's a complementary function. It's reflected. Not that. Look at the value of a logit for 0.99, 4.6, right? Why am I saying that? Right? If you get a main effect or if you get an item intercept and it's -5, what's that tell you on the logit scale? Like transform -5 to a probability. You're down here at 0.001-ish, right? That's all. I want you to think about the size of these parameters because the size will indicate where the probability is, right? But think about it. Anywhere between 0.99 and 1 is a logit that's bigger than 4.6. How many of you have done logistic regression and looked at logits bigger than 4.6 before? That's a big effect is what I'm trying to talk about, right? The magnitude of these numbers have meaning for probabilities. We usually get away from that in logits. If we're only looking at logits, we sort of forget that. We always have to try to back translate it. And so you know all about that. All right. How's the pace? Too slow? Too fast? Goldilocks? Just right. All right. Let's imagine I have an example item, 2 + 3 - 1. I've been using this all year. It measures addition, it measures subtraction. Those are the 2 latent variables. Actually, here, addition and subtraction are 2 types of latent variables. Imagine a basic math test where you had addition, subtraction, multiplication, division. We can easily see that. I don't think that's a very good test, but let's imagine that's what you have, right? If you have an item like 2 + 3 - 1, we're going to treat addition as being a class. You're either high performing or low, master or not of addition, high performing or low of a subtraction. So now we have 4 types of people. People who are low on both addition and subtraction, people who are high on addition, low on subtraction, people who are high on subtraction, low on addition, and people who are high on both, right? So now we can build a linear model. If we dummy code these attributes, here's what we get. We've got an intercept, We've got a main effect of addition, we've got a main effect of subtraction, and we have two-way interaction between the two. And this model right here, let me go through the notation and I'll go back and set for it, is ugly. Look at those. Why is it so ugly? Well, let's talk a little bit about it. Logit of a correct response is here. The intercept, same ANOVA interpretation, only on logits, right? This is the log odds of a correct response for people who are not masters of addition and not masters of subtraction, right? By the way, I'm just going to say master versus not today when it comes to the attributes. I've already disqualified, but it's easier to say master than high performing and low performing, right? So could I just say that? Somebody who's mastered this versus not? Agree to disagree that it's not really the right word, but it's easier to express in this lecture. So again, that's our intercept. It's when all the predictors are 0, that means someone who's not a master of addition, not a master of subtraction, right? Turns out, in ANOVA, if this was not a logit, that thing would be the mean of the group, right? Like our ANOVA function, if we have a balanced design, and that thing right there, that's the mean of the group right there, right? Again, balanced design. You get weirdness if you have unbalanced n counts and so forth. But we can think of it that way. Turns out the mean, if we could observe whether a student was a master or not of subtraction and addition, this would just be the logit transform mean of that group. It's like an item mean. For everybody who's in that group, that's the mean. All right, the main effect, this thing, is the conditional main effect for addition, which is attribute 1 right here. It's the increase in the logit for mastering addition. Now, I say this word increase on purpose. In ANOVA, the means could be up or below, higher or lower. Here in the LCDM, to make things work the way we need to, we're going to make these have to be higher, equal to or higher, monotonically increasing. So this is the increase in the logit for mastering attribute 1 if you have not mastered attribute 2, right? So people who have mastered addition but not subtraction, this is the increase in their log odds of a correct response. That makes sense? Similarly, the second one is the conditional main effect of subtraction. It is the increase in the logit for mastering subtraction when you haven't mastered addition. Right? Now remember, conditional. Conditional means we have to say something about the other interacting variable. Right? This is only true when alpha 2 is 0, or when alpha 1 is 0. And finally, the two-way interaction is the change, not the increase, but the change in the logit for mastering both. And we'll see in a little bit why I say increase for both of these and change for that one. This one actually can be negative. Not completely negative, but mostly negative. It actually depends. How are we doing so far? Latent variable ANOVA. Who thought you wanted to do that, right? All right, now what are all these notation things? Well, it turns out people in IRT had it great, right? First of all, they named it item response theory. How much better of a name do you get than that? Like everything's item response. Now we have to say this stupid theta is the theory? Anyway, no. Everything could be an item response theory, right? And not only that, with a single dimension, you can name parameters like A and B and C, right? That's great. Now imagine you're trying to come up with this model and you said, okay, I've got any number of dimensions. Oh, and there's that Q matrix. So I may have 6 dimensions overall, but this item might measure 2 and the other item might measure 3, right? So the way that we came up with this notation scheme was to try to denote all the different layers of each item, right? So this lambda represents an item parameter. Lambda for me is like a loading of as a fact. I tried to map this onto factor analysis. Lambda I. The E is the level of the effect it applies. So when you see a 0 in the second spot, that's the intercept. A 1 is a main effect. A 2 is a two-way interaction, and so forth. And if you see a parenthesis afterwards, it's the attributes to which that effect applies. Right? So it could be a 1 or 1 and 2, 1 and 3, and so forth. So if we go back to this other slide, lambda I0 means this is the intercept of the ith item. Right here. And then lambda I11 says it's the item i's main effect of attribute 1, going in that order, right? I is the item, 1 is the main effect, attribute 1 is to which it applies. Okay? Item I12 means item i's main effect of attribute 2. And finally, I212 says item i's two-way interaction between attribute 1 and attribute 2. Question?
No, I just realized you were saying itemized.
Item I. Yeah, I know.
It just did. Yeah.
I'm sorry.
It's me.
No,
You.
not at all. It's always me, and I'm okay with that. Yes. Question? Please, please.
Why did you guys decide to include the second number, the 1 and the 2? That tells you how many interactions when you can just tell.
What happens when you have a three-way, an item measuring 3 things? How many main effects? 3. How many three-way interactions? 1. How many two-way interactions? There are 3. Right? So what we end up getting is this crazy quadratic expansion of interactions in between as the number of attributes grows, and that's why. Yeah. This notation, by the way, I'm really happy with how we came up with this. I'm really happy with the result, but when you show it to somebody, yeah, we're not dealing with A's and B's and C's because an item could have 3 two-way interactions on it, right? When you start going multidimensional and allowing the item to be multidimensional as well, it gets complicated. Not to say that multidimensional is complicated without items being multidimensional. Other questions? Some notation there, isn't it? The other part of the notation that I haven't figured out yet, and maybe one of you can solve this for me. If you didn't have a fully crossed model, how do you notate all the possible ANOVA models that could be there? Why I mention that is, if you had a nested model ANOVA, like if you had to learn addition before you learned subtraction, think of how this line would change, right? This parameter is the main effect of addition for somebody who hasn't made a master subtraction. So that's okay, that stays there. But this parameter is the main effect of subtraction for somebody who's master subtraction but not addition. Now, if you had to learn addition before subtraction, which is seemingly what happens, because you got to know a little bit about numbers and properties of numbers, we wouldn't be able to estimate that because there should be nobody in this group right here. So what ends up happening is that this thing gets knocked out in a nested model. In the model, ANOVA model itself with a nested factor, factor 2 would be nested in factor 1 here, and that would be gone.
Would you still put it in your model to see if it does actually become 0?
Yes.
Or if
Yeah.
there's something, yeah.
Yes. Well, it depends on context. In most of the context that we've done in this class, yes.
If you want to see if it's true or...
That's right. That's right. If I ever do teach that class on DCMs again, I can go long, deep into that. But yeah. Other questions? It's break time. So think of your questions over break. We'll come back in 10 minutes.
I think it's a quick announcement.
A quick announcement.
So on the discussion board in Icon, there's an editable party list for setting up. And you should be able to...
We're back. Any questions on what we covered to this point? Let me ask you a question. Regurgitation question. Repeating question. I don't know why I have regurgitation. Why would someone want to use a DCM?
They want to get at latent category.
2 thoughts. They want multidimensional information, number 1, and they want somewhat reliable classification. That's it.
I think philosophically too, I don't like it's better to know if somebody is able to do something than to pit everybody against each other for the highest score.
So there is an interesting part of that, and then being in the DCM world where we don't technically have the scores, right? There's no thetas that come out of this. It's literally probabilities you're in each class, right? Being in that part of it, like I work with a couple school districts pretty closely, and when I show them scale scores, everybody's like, what am I going to do with that? Like, what am I going to do with a theta? Like, there's something about adding even an arbitrary threshold to it that goes beyond it. By the way, speaking of arbitrary thresholds, how did the standard setting thing go? How many of you went to that? You know how to set standards now?
No. How to maybe make standard setting process better.
Here's what I'm going to make a point of this. So here's our continuum again. What's standard setting doing?
Deciding to cut.
So if you believe in the continuum, there's no mathematical basis for any cut. Got to remember that in standard setting. That's the thing with our world that we did. And the thing that you don't hear about when it comes to it is if all you were interested in was the classification, you'd never build a test to scale people in the first place. But people in the field don't ever say that or do that. The other thing I would tell you about standard setting is it's a human, so it's no longer mathematically, there's no mathematical basis for setting a standard. None. Right? Because mathematically what we have is a continuum. And what we can show is that anybody who's a plus or minus around the cut are almost identical. There's no quantitative or qualitative difference about them. So therefore, there's no reason for a cut to be there with the exception of an arbitrary need for it later on, right? So just remember that when you're doing standard setting. It's a whole bunch of waving our hands about trying to make numbers, but there's no mathematical basis for a cut score at all, right?
Well,
Huh?
and something Wanchan said to us is that often they spend all these days on standard setting, and then the powers maybe in the end go, well, yeah, you did that, but we're going to put the...
Oh, let me give you the other one, right? I did a standard setting in 2006 with Kansas, when I worked at Kansas the first time. And I was there as part of I was helping with the room of people and panelists and stuff. It was a 2-day process, right? There were panels separated by grade and by content area. And it was a Thursday and a Friday. And I mentioned Thursday and Friday because guess what happened at Friday at noon? Everybody drove from all corners of Kansas to get to Lawrence, right? Lawrence is a long way away from the western part of the state. And everybody's like, yeah, we're going to put the cut there. See you later. We're gone. So there's 2 parts of standard setting I always want you to remember and never talk about it. Number 1, there's no mathematical basis for it. It's completely arbitrary. And you'll hear people say, acknowledge that. It's arbitrary but not capricious is what they'll say. You ever heard those words? It's like we had a process involved. So what is it? It's a human decision process. Turns out I used to be in this literature my first year, couple of years in grad school in judgment and decision making, which studied human decisions. And very little of standard setting is informed by that literature, and it drives me crazy. So when I see standard setting and people doing it, I'm like, oh my God, how humans work in groups is what you need to study, and we're not doing that. We're talking about trying to make up a mathematical basis for something that has none. So anyway.
Are you talking about decision trees?
No, I'm talking about like Tversky and Kahneman, or Thinking Fast and Slow, that book. I don't know if you've seen the book. I don't remember who wrote that. Is it Early who did that one? I don't remember. Anyway, there's a whole like field of, it's almost like somewhere in between quantitative psychology and social psychology, describing how people view and make decisions under uncertainty, right? And it's sort of the heuristic algorithmic biases in people, kind of like how our brains are structured to perceive probability and so forth. Like when I was editor at JEM, I actually tried to publish. I published one of my former advisor's papers, actually. Didn't get reviewed well, couldn't find reviewers. But I kept on trying to find people like, let's bring the decision making to the standard setting, because you don't hear it. Right? You hear Angoff or you hear bookmark, right? Did you cover those? I'm guessing. What else? Anyway, modified Angoff, modified backwards bookmark. I'm just kidding. Triple Lutz. Anyway, point being.
Is that a nice getting move?
Yeah. Thank you. Thank you. Maybe a sow cow, right?
Yeah.
Yeah. Sorry. Going with. I got some breadth in what I know. Maybe not. Ask me about my ice skating. No, I'm just kidding.
That's Jeopardy knowledge.
That is no. That's just me embarrassing myself yet again. But
Part of the Winter Olympics.
yeah, that's right. That's right. The point I'm trying to make is, and why I'm drawing this in, I'm really pleased that you got the workshop, the skills that you need to know. Just remember that as you're going, because standard setting is always there. But why we need it is getting back to the point that we were getting to is sometimes it's a lot easier to make this is the information what to do with that score, whether that's licensure or not, whether that's proficient or not, or whether that's help me or not. We always have to ascribe that to it. The score itself doesn't help us with that. It doesn't tell us that. And yes, some of the methods that you use in standard setting at least give you some quantitative information about the ramifications of where you place that score. That's good. I don't disagree with that, but I do want you to remember that standard setting is arbitrary. Please do. Yeah.
This comes up with intellectual disability because even though a child might test at 70, you still have to have all the additional information to decide whether they're truly intellectually disabled.
Yes. Oh, it goes even further than that. You think about, so the standard setting process, I'll give you a comparison that's not standard setting. And I'm not speaking from being an expert here, so I'm going to caution with what I say take this to be just from me perceiving that Lisa used to work with some people who did, what's SLD stand for? Specific language disorder, specific language disability, learning disability. Anyway, students who had very specific like reading difficulties. So they'd administer these assessments. Often these are little kids, so they'd be, person-guided assessments like school psychologists or otherwise. And then arbitrarily they decided anybody at the 25th percentile or below needed help. There's your arbitrary standard setting as well. That's how they function. So same type of thing. It's not entirely the case. So in many ways, the diagnostic model is yet another way of doing a standard setting. It's just we don't know where that line is going to be drawn or why it's going to be drawn. And that's the subject of some work I'm doing right now that I'm not willing to share, but that's part of it, okay? It's part of why I don't like these as much anymore, but that's good. So anyway, yes, why we do DCMs. We can get classifications on short numbers of items where the classifications are fairly consistent from time administration to administration. Right? So we have some type of reliability, and perhaps that classification is instructionally relevant. But that's a big if. Okay, let's do some numbers, shall we? I put numbers to this: addition, subtraction, multiplication, division. Imagine the intercept's -2, the conditional main effective addition is 2, the main effective subtraction is 0, and the two-way interaction, 1, positive 1, main effective subtraction. The two-way interaction is 0. Let me ask you, if this were IRT model parameters, what would our probability contours look like with this set of parameters? Straight lines. And that's because the interaction is effectively 0 and not in the model. It's an additive model in this case. Right? It didn't have to be. I'm just hypothetically telling you these numbers, right? But here's what it looks like. Here's our 4 different permutations of attribute 1 and attribute 2. This is the item response function with plugging those numbers in. Here's the resulting logit and probability for each. And I'm saying that because, unlike an IRT where you have to plug in theta to get your probability, there are only 4 types of people on this item based on this model. Each one has a discrete set of probabilities. I'm going to go a step further. Here, this is our logit response function right here. This is -2 for the intercept. This is alpha 1 and alpha 2 on each, right? So each permutation is a section of this bar chart, and the red line is the logit. And then if I convert this to probability, you get this. And I made an offhand comment once in a talk. I was like, you've heard of the item characteristic curve where you have the probability based on your continuous theta, right? Like this. I'm trying to draw the curve backwards. Well, the analogous chart in DCM world is item characteristic bar chart. There's no curve because there's no continuum, right? There's only types of people, and that's a bar chart. So here, we got 4 types of people. We have the 4 probabilities. Things look good, right? We could also, yeah, question.
Sorry, but yeah, in the previous slide, you had your estimate for the interaction equal 0.
Yes.
But then you are adding one logic there, and we can see that the
Ooh, yeah, it's a 1 here. Wait, hold on, let me see.
that's the interaction, right? So
Oh, no, it's not. So this is still 0. This is -2.
yeah.
That's 2. That's 1, and that's 0. So -2 plus 2 is 0, plus 1 is 1, plus 0 is 1.
Oh, okay.
Yep.
So what's the meaning of that column there?
The logit column?
Yes.
That is the sum of all the parameters times a 1 or a 0 based on the permutation.
Okay.
Right? That's their expected logit for each type of person for the item.
Great. Thank you.
Thank you. Other questions? No questions. All right. Let's talk about interactions real quick, shall we? This model, remember this plot in ANOVA class where you plot the means for each group? We could do that too. I remember ANOVA way back when. We taught it in a while, but when it looks like parallel lines, no interaction, right? Interaction? Yeah, not parallel, right? But turns out this is one of the models that existed before the LCDM. The compensatory RUM is what Sarah Hartz called it. Jim Ateliatori renamed it additive CDM, whatever you want to call it. By the way, RUM stands for Reparameterized Unified Model, which I won't even get into. That's what this is, right? It's just a 0 interaction. It's just basically the straight swapping of your MERT model without interactions, the theta being multivariate normal to multivariate Bernoulli. You could also have something that look like this. Look at that interaction, right? What does this tell you? Well, when alpha 2 is 0 and alpha 1 is 0, you're here. When alpha 2 is, when alpha 1 is 1 and alpha 2 is 0, you're here, right? When alpha 2 is 1 and alpha 1 is 0, you're here. And only in the case where an alpha 2 and alpha 1 are both 1, you get a bump in probability, right? So here, if you look at the item characteristic bar chart, you've got nope, 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 way high probability, right? This is not a compensatory model. This is a non-compensatory model, meaning, remember the definition of non-compensatory. Like if you lack in one trait, you can't make up with the other, right? So think of it this way. Here, if this truly was non-compensatory, you'd say, oh, you need both attribute 1 and attribute 2 to get a high chance of answering the item right. And in any one of these other patterns, one or more of them is 0. You have not mastered it. So it's a low chance of getting it right. Turns out this model is called the DINA model. DINA model is a conjunctive model. It's all or none. Let me just double check something here. Nope. And I'm going to dive headlong into it here. It turns out the item response function for this, which I really wanted to explain here. If I just do the logit, right? If we had 2 attributes, right? I0 plus lambda I. Second main effect, and then the 2-way interaction I. Right there. This pattern can only come about if this is 0 and this is 0, leaving only lambda 0 plus lambda I 2 right there. So let me ask this question for you. By the way, DINA model, if you read the literature in diagnostic models or cognitive diagnosis, this model shows up everywhere. Honestly, I wish it would die. Death to DINA model. Not that anybody named Dina, you know. Right? Right? I just wish DINA would die. But here's why. Right? Imagine you're not in psychometrics. Imagine you are doing ANOVA. Right? In your ANOVA class, if you estimated this model, why is that not a good idea? Right? Or better yet, if this interaction is not 0, significantly not 0. Fitting this model by itself has up to 3 different possibilities for confounds as to why that's the case. Right? So going back to ANOVA and linear models and regression, here's that interaction. And if we have a main effect, we're controlling for the effect of the main effect of the variables. In the DINA model, that interaction is 0 for all the variables except for the highest order interactions. So we're not controlling for those main effects. So what that means is if we have a non-zero parameter here, and it has to be positive for the constraints I haven't told you about that we're getting to. So either this is 0 or it's bigger than 0. If this is bigger than 0, it can be bigger than 0 for multiple reasons. One is truly that these latent variables do have an interaction. That's the one that's good. But there's other reasons as well. What if the item had main effect being positive of attribute 1 and a 0 value for attribute 2 for the main effect and a 0 value for the interaction? Turns out that interaction is also positive because you didn't control for the main effect. Right? Similarly, backwards, if attribute 2 is positive and attribute 1 is not, and the interaction is not, that thing's going to be positive as well. So the reality of it is if you do a DINA model, it's like you run around going, yeah, I do ANOVA living on the edge of ANOVA. What's living on the edge? Only the highest interaction. Forget the lower order terms. Who does that? How many ANOVA models in your ANOVA class, or whatever ANOVA training you did, that had two-way interactions, had no main effects in them? Have you ever seen it? It's lunacy, right? It's like, hey, in the context of linear models, we figured out long ago that's a bad idea. Yet in the context of psychometrics, now when DINA came out, it didn't look like this, so we couldn't tell. But now we know it looks like this. And you got a bunch of chumps running around running DINA. Sorry, that's what you do. If you run DINA, you're a chump. I'm just going to say it. All right? You got a bunch of chumps running around running DINA who are being like, yeah, forget the main effects. Who needs those main effects? I don't know. Can I say that? Psychometric chump? Is that good? Can I define that term now? Instead of like telling people a DINA needs to die, I'm just going to call you a chump if you run it. Chump. Anyway, sorry. I don't even know what that means. Is that a good word? No, never mind. I don't even want to define it. Never mind. I know what it means. Never mind. Looking for a put down that's not all that bad of a put down. But, so, someone talking to me. Anyway, how am I doing? Does that make sense? So DINA, this model right here, don't do DINA, please. And if you've done DINA before, you're not a chump, I promise. But if you do it in the future, no. Okay. No? You like that?
Well, did you know that Ahmed's wife's name is Dina?
I do. I do.
I don't know. This whole thing.
But how does she spell it? Does she spell it DINA?
Yeah, same like that.
But she, your wife, who I've met, that's why I pointed to you. Like I'm not talking about the person.
I told her before.
Anybody named Dina is totally cool. In fact, I love the name Dina. It's a great name. Just the model is a bad idea.
It just makes the whole rail a little weird.
Yeah, well, I think of like, there's a colleague of mine, I really like her work, her name is Dana Pastor. So every time I think of Dina, but she spells it D-E-N-A, I believe. So, but no, I'm not trying to this is no violence toward anybody, and this is no putting down of the name Dina at all. Got me? Okay. So I'm forceful about that. Look at this one. Oh, no. Who's that guy? Oh, shit. Okay. So yeah, back in the early days, this is the flip of Dina. This is Dino. Because I like the Flintstones, like Dino. You know the dinosaur? Never mind. Anyway. Dino. So this came about because at the time I was doing the gambling paper with Bob, we only had Dina. And we're like, okay, we're modeling terms from the Diagnostic and Statistical Manual of Mental Disorders, DSM. And they had things like, I think about gambling a lot, and it was one attribute. Another one was, I have committed illegal acts to finance my gambling. All right? So there was an item that measured both, right? Because thinking about it certainly precludes committing illegal acts for gambling. So looked at the DINA model and I'm like, this model says to answer this item affirmatively, you need to both think about gambling and have committed illegal acts. I don't know that really fits well with it. Maybe one or the other or both. And that's what DINO came from. The DINO model. By the way, the DINA and DINO stands for deterministic input, noisy, and gate. It's sort of a switch analogy. So you have a bunch of, if you're going to have current in like an electrical system, you need to have all the switches on for the current to flow. That's how that works, right? Deterministic inputs, noisy, or gate is what DINO stands for, meaning all you need is one switch to have power to have the current to flow rather than all of them on. That's the difference. So there's like an engineering term to both of these, but don't let them fool you. Bad science, bad science. This model is also interesting. It's one or more, right? Meaning if you meet one or more of these things, you're likely to say yes. If you don't meet any of them, you're likely to say no. We found that to be a little bit more plausible for the gambling data, because the gambling items seem to imply that. But, when we were doing this, honestly, this paper started in like 2003, right? It took forever to get published. We had to write our own MC algorithm for it. It was nuts. It was in Fortran too, right? So, anyway. At the time, once we did that, we're like, you can switch the model up, no problem. But I can't expect somebody to know which one's which, right? By the way, the pattern of main effects and interactions on that one, lambda 0, I'm just going to abbreviate this quickly, okay? Can I just do that? Okay. The way this works to make this item response function fly is that if I, if I take off the subscripts, so I just have one parameter here, a lambda, and I remove this, and I do this right here. That's what it looks like. There's one main effect. It's the same for both attribute 1 and attribute 2, or I should put alpha 1, alpha 2, alpha 1, 2. But the way that works out is if you have alpha 1 but not alpha 2, this is alpha 1, alpha 2. Okay. All right, that's there. If you have alpha 2 but not alpha 1, that's there. It's the same one. But if you have both, now you have two lambdas here, you got to subtract one off. So it's a pattern of constraints on parameters as well. Now, you might think this is trivial, stupid diagnostic model work. And yeah, there's a lot of people who believe that, and that's probably true, some of it. But what I'm getting to is the point of the LCDM paper, is that we've just seen several different styles of model, one of which that was compensatory or additive, one of which was non-compensatory, and one of which was also compensatory. These are the polar opposites. This is very compensatory, meaning you can always make up for one attribute. And this is non-compensatory, meaning you can never do it, right? These are the extremes. And all those extremes come about by playing around with model parameters in the same linear model. And the lesson to take from that is not which DCM to run. It's how you look at MERT models with multiple latent variables as well. Because the same distinction of compensatory versus not that we talked about 2 weeks ago with MERT, with the contours and the lines and stuff, boils down to this right here. So that's cool, right? So now MERT models with interactions, to me, is an untapped, beautiful area of research that people could go into fitting with this. I think that's a beautiful place to go. But that's just me. There's a lot of other people who think different things. All right, here's the reality though. This is extreme in that there's no interaction. It's precisely 0. This is extreme saying there's no main effects. This is extreme saying they're all one parameter. What's reality based? That. Somewhere in the middle, right? This is a model where you see a slight positive interaction, meaning there's a slight benefit to knowing both attributes more than just knowing any one of them singularly, right? Sort of like a benefit, the whole being greater than the sum of its parts, if you think about it that way. That's LCDM. That's each model parameter being estimated. So, this whole discussion here like if you read the GDINA work and you read a lot of people's work in GDINA, it's which model fits better. Is it DINA? Is it DINA? Or better yet, which I'm going to go estimate like the LCDM or the GDINA. I'm going to go see if I could make it a DINA or a DINO. I think that's dumb. I don't think that's a good idea because it doesn't matter what this is, except for we need this to be accurate, right? Whether or not the interactions are positive or negative, whether or not the main effects are 0 or fixed to be equal, does that really, do you really care as a person who's trying to measure somebody or classify somebody? No. What matters is the model fits. And this model will end up fitting better than this model or that model or this model because, as you see, I started with the same place, right up here. The LCDM, that thing right up there is LCDM. I do these constraints, I get DINA. I do those constraints, I get DINO. I do this other one, I get the additive version of it. They're all part of the same thing. And guess what? That's all part of how you estimate. So that's what I call models being subsumed into it, right? If you can arrive at DINA, even though you used LCDM to estimate it, that means DINA is subsumed by DINO, by LCDM, right? But I tell you all that not for having you figure out what structure your data are, because nobody cares, honestly. Whether they're compensatory or not a big deal. That's the least of what we try to do, right? What people care about is whether this is an accurate depiction of what people know. And to do that, you need the best fitting model. Cool? The other part of it is if you start reading studies about DCMs, and you're like, well, I fit the GDINA, and it looks like we're closer to DINA versus DINO. It's like snore. I don't care. What does that tell me about the phenomena? It doesn't tell me much, right? I don't care. All right. Wow, I capitalized form. I am becoming an old man. General form of the LCDM. Gosh, no. All right.
You're not that excited about it?
No. If you go and grab the article, the Henson, Temple, and Wilsey, the one with Bob and John, Bob, John, and John. I was going by John back then. Don't call me John, please. Don't call me John. That thing doesn't look like what I just showed you, right? There's a general form to it because, remember, when you make a psychometric model, we need a model that applies for any Q matrix, right? And so all the Q matrices you've used in this class have had only one dimension per item. That needs to be part of it. If we knew that Q matrices did that, we wouldn't have any interactions because we'd only have one main effect per item and we wouldn't need the notation. We could just use A's, B's, and C's, whatever, no big deal. But the notation is much more messy. That's the model. That's an adaptation. Matthias pulls the intercept out of this. But basically it's this. We have a profile of possible item parameters in lambda. That's a vector. And I'm going to unpack these in just a few slides. And then we have a combination function. Matthias called this a helper function of the Q matrix for that item and a person's profile of their own mastered attributes, zeros and ones. So what happens here, right? So the key to understanding that is this is a general form. Again, it's a general equation that takes any possible number of attributes. This Q matrix is anything, right? All we know is it's for one item. It has a series of zeros and ones in it. All of them can be one. All but one of them can be one. If it's a zero, actually, all of them can be zero. It's fine. So let's keep this in our context. Let's do addition, subtraction, multiplication, division. That's a vector of size 4 right here. This is a respondent profile right there. And here's our item 2 plus 3 minus 1. That's our Q matrix entry for it, that row vector for it. So that possible parameter vector lambda I, if you think of it, it's possible. And this is where you're going to be like, really? A DCM? If we have a test or an analysis with a Q matrix with 4 columns, 4 attributes, and an item were to measure all 4, there would be 16 parameters for that item, right? Now, compare that to your IRT model. Oh, yeah, A, B, and C, right? You got to get 16 characters down the alphabet. Oh, my G parameter, it's all screwed up. No, dude, look at your F. Anyway, no, it's not. You know what I'm saying, right? It's a lot. I'm trying for humor. I'm trying to make this at least. I had psychometric chump today. I think that's pretty good, right? Those are people who use Dina still. That's all I'm saying. If you didn't know any better and you used it, you're still not a chump. It's okay. I've used Dina too. Look, I've done it. All right. So here, this thing is all the possible parameters that could be there. But we know for this item that measures addition and subtraction, there should only be 4 parameters, right? There should only be the intercept, lambda 1, 1, lambda 1, 2, and lambda 1, 2, right here. 2, 1, 2, excuse me. Right? There's our intercept, there's our main effects, 2-way interactions in higher orders. So, what this helper function does is it builds a set of 1s and 0s based on the Q matrix and alpha. That's the product of all of the element-wise product of all the attributes. Did I do something wrong?
Oh no.
Okay.
I was cracking my neck and looked at her weird.
Okay. Thank you. I'm over here feeling self-conscious.
No. It was
Dropping the ball on, whatever.
Just be eye contact.
Hold on.
No, that happens.
I'll just join the line. There we go. All right, feeling better.
I really hate that noise.
Stretch. You should ask Lisa Hoffman to do some.
It's on your toes.
Sorry. By the way, because I mentioned her multiple times in class, how many of you still have Lisa as an instructor? Anybody? Do me a favor, any of you who go to Lisa's class or if you sit in, ask her to pop one of her joints for you. Stupid human tricks with Lisa Hoffman. Sorry, no. Ask her. She'll get the hips really well all the time. So see if she'll do that.
Is that Ehlers-Danlos?
I don't know. I don't know what that is. Anyway,
Probably.
what is this helper function doing? It's taking the element-wise product of Q and alpha across all of it, right? That's it. What is the result of that? Right? If Q is a 0, which is the Q matrix, that means this value will end up being a 0, regardless of whether or not, for instance, this 2-way interaction of attribute 1 and attribute 3. Attribute 1 may be a 1. The Q1 is all definitely a 1 on this item. Attribute 1 may be a 1, but QI3 is 0. So this has to be 0, right? Now remember, in the form of the model, this is a dot product, an inner product, matrix product, right? So what that means is that what we're going to do is take the value of this and multiply it by the value of that in forming our item response function. So we turn these into numbers. We can see the patterns of zeros knock out all the parameters that don't exist on the item, thereby establishing the notation that we need to fit any Q matrix. And in general, you can describe it this way as well too. But the result of this, because we have a 16 by 1 vector that's transposed, that's a 1 by 16 times a 16 by 1 vector valued function, it gives us a scalar number. That's our logit. How are we doing? Question?
Yes, quick question. So can you go back to the previous slide, please? Because there we have that parameter vector, but you also said that we could reduce the number of parameters we are including.
Correct.
Should we do that before estimating our model or after we have the results?
That's a great question. Theoretically, you should estimate the fullest model first, look at those interactions and see if they're non-significant and remove the ones that aren't. That's the theoretical answer.
Okay.
The practical answer is estimation's still very hard in the LCDM. And it doesn't work always. Sergio, you've been using EL Plus for this, right? Have you had it fail on you after a while?
A couple times.
Yeah. So in practice, you may set about to run the full model, have it not converge, and then have to make it simpler to make it run also. So the theory says if we were just doing this as ANOVA, yeah, fit the full model first, because ANOVA we can almost always estimate unless there's we can't invert our X matrix, but X transpose X, can't invert that. But point being, this thing, practically speaking, I'd try the full model first, and if it didn't converge, I'd reduce it. If it did converge, I'd look at the parameters and potentially reduce it. Most studies don't go that far, though. That's like fitting it into the linear model world. But what you know about ANOVA should serve you well to guide you here. Other questions? Thank you for the question, by the way. Okay, here's our subsumed models again. I mentioned this before. I already went down this path, so I can actually move this pretty quickly. You may see these names, though. DINA, NIDA, which is noisy input, deterministic AND gate, reparameterized unified model, DINO, NIDO, and CRUM. Yeah. Anyway, basically all of these are subsumed into the LCDM. That's what this is saying. This is the pattern of constraints, but here are the functions again. And I did add, I totally forgot it. See again, this doesn't have an interaction. This doesn't have main effects. DINA doesn't have main effects. DINO has the same main effect and two-way interaction, and the two-way interaction is -1 times that. And then so on and so forth. The reparameterized unified model is really intense. That's actually where I started my work with Bill Stout long ago. That one, I think Hans Friedrich Kohn and Shai Shu had a paper where they derived how you can get the parameters from LCDM as well too. But it's lots and lots of algebra. It's crazy. But what I'm getting at here, again, is not these models existed. What I want you to take from this is, if you're in a spot with a MERT model, with an item that measures more than one trait, right? There's the best way to specify potential non-compensatory is to put the latent variable interaction in the model. And if I meet my goal this week of developing a lecture for next week and a homework, that'll be one of your homework assignments, is we're going to estimate a math model and an English model. We're going to have the English and math items have both English and math on them, because some of them are word problems. And we'll have an interaction, latent variable interaction between the two. That's a harder thing to do, but I'm going to try it. We'll see how that works. All right. Latent variable interactions, by the way, as I mentioned this here, is a field in psychometrics. The whole field. They're like this tiny, right? Like the CFA people talk about them. But they come up with weird models also, like they had to have a product of variables to be an indicator of the interaction. That doesn't make any sense either. Okay, so it's this weird spot. If any of you are looking for an interesting research area, it's here, I think. The latent variable interaction is incredibly difficult to estimate, but incredibly informative and powerful, I feel like. And think of it this way. This is a possible result. It's not likely. We usually will see a set of parameters that have small main effects. So slightly off of this with a positive two-way interaction. But think about what that means. Like, I have a project right now where I have a couple standards. As these districts I work with, they're trying to see if the standards that you learn, in the first part of the year impact what you know when you're learning in the second part of the year, right? And what's important to them to know would be, do I have an interaction between standards in predicting how you do on an outcome later on? And this pattern might be there, right? This pattern of interactions would be really informative, meaning both of these standards are gateway standards to learning something later. Like we talk about algebra being a fundamental quantity to learning later math or being in STEM education. That's a hypothesis we can build and test psychometrically. Like, this builds a modeling framework to do that, not just the DCM part, but what you're thinking about it when it comes to the pattern of interactions would apply in MERT or in other places as well too. And I think that's really powerful and really important to think about as well. A lot of what we want to do in psychometrics right now is held back by people not knowing the quantitative methods to be able to do it, or the quantitative methods not being there. It's here. It's hard right now. It can get a lot easier, but it's possible. So, anyway. Question?
When we think about the visualization of that interaction,
Mm-hmm.
kind of drawing back to Lisa's generalized path diagram.
Yeah. Pardon me.
Is there an arrow that denotes that interaction?
No. No, that's the hard part. I've tried. I can find some slides if you want. Here, do you want me to try to find? Hang on one second. If not, then I'm going to just keep going with this lecture next week, and I don't have to stress as much. But yeah, it's. No, that's not it. Give me a second. Let me see if I can find it.
What's running through my head is that covariance line, but that's not
Yeah, no, that's not it. It's hard to. So the path models that you've seen before. This is a great question, by the way. Path models you've seen before are main effect only. Always, almost always. Oh, that's not it. Dang it. I might be able to find it here real quick. Let me just.
Remember there being dotted lines as well, but I think that refers to the magnitude of the effect rate.
Here we go. This. So, when I draw these as a path diagram, here, look, 2 plus 3 minus 1, right? I used this example since 2004, right? Addition, subtraction. By the way, those of you doing job talks, that was my first job talk. And Bob Henson's first job talk, way back when. I took this from Bob. So this is the path diagram we're talking about, something like this, right? Normal, latent variable path diagram. Here, give me 1 second. Nope. I want to show the animation. That's why I'm going to get PowerPoint out here, okay? I'll see if I can show the animation. All right, so this is what we normally do, a unidimensional model. That's a path. That's our latent variable, circle. Squares are observed variables. We have our arrows indicating what's being measured. That's sort of it. Now, if we did things with a MERT model, we'd have 4 latent variables. I like to think of these latent variables as having a cut point, so I bisect them. I put a line in it. And then that would be our MERT pattern, right, where addition and subtraction both measure attributes 2 and 3, right? Division here, addition and multiplication on that item. But to indicate the latent variable interaction, it's really a product of these variables. And the only way I could do it was to divide, like add a dot where they were both colliding. Because if you think about it, that line we often put, like when we show a path diagram like in text, we will often put the loading on each of these lines. To show the latent variable interaction, we'd need to put the loading on that third line right there, which is really the product of both. But this is where path diagrams really start to break down.
Yeah, I guess that has me now thinking about like what happens to that error. Is it partitioned or assumed to be partitioned?
You mean like if this is if there was an interaction but it's not there, or you're thinking of the error term itself right here?
Yeah.
So the latent variable interaction we're talking about is an item parameter, so it's part of the measurement model, whereas the structural model itself of the latent variables is separate, right? And so now we can show that.
Sorry for going down a rabbit hole.
No, that's okay. That's okay. I'm trying to. So the structural model I haven't gotten to in this. Turns out it's the same structural model that we had last week. The proportion of people with each attribute pattern. But because we have very specific meanings to the attributes, right? We can take that profile of the attributes themselves and map that onto the marginal proportion for each attribute. We could also map it onto the two-way contingency table. In fact, again, I'm going back to multivariate Bernoulli. You remember the M2 discussion? We said the target distribution was the probability of any pattern or a response pattern. If we look at our structural model, it's the probability of any attribute pattern. It's identical. It's a multivariate Bernoulli thing. And so therefore embedded in that multivariate Bernoulli are the one-way, two-way, three-way contingency tables of probability as well too, from which we can then gather it. But the ramification of that is that the path diagram is actually inadequate to describe the structural model because it's possible, right? The path diagrams with correlated terms, the bidirectional arrows, the one with the arrows at both ends, describe covariance, which is a two-way table. But we could have a three-way effect for addition, subtraction, multivariate multiplication. Now, how we can't depict that? There's no three. A line only has two ends to it, right? So, I'm glad you asked the question because it does. We do separate the structural from the measurement. This is sort of measurement here, and what happens with these is structural, but we can't depict all the parameters in it. with 4 attributes, there's 16 parameters in the structural model. Right? One for each. There's 15 we estimate, and the 16th makes it sum to 1. There's a probability for each. If you compare that with what we do in a latent, like a CFA or a MERT model, we'd have all pairs of interactions, which I think 4 choose 2 was that 6? 4 choose 2 is 6, right? So we have 6. So there'd be 6 parameters plus 4 means, which we usually fix to 0. So maybe 10 parameters total. So this structural model is much more parameterized in the DCM. Thanks.
Why not 4 choose 2 be 12?
4 choose 2 is not 12, I know that much.
Yeah.
Yeah.
Now that you have that picture there, so this is our model, right? And those arrows represent now what's the effect of each of these things
Right.
on the probability of having a correct response for that specific item.
Correct.
So once we have this model, we can use those results to estimate the probability
Oh, yeah.
of each subject to be classified into
Yes.
any of the
Just like,
categories we have.
just like in IRT, if you quote unquote calibrate your model, you get your item parameters. In our case, it's not just the item parameters, it's the structural model too. You get both of those, you go back to the latent class model function and you build the same probabilities out of it.
Great.
Absolutely, yes.
Yes, follow-up question, because now if we have calibrated these items,
Mm-hmm.
so if we want to, well, if we need one test to classify people, should we select our items based on some kind of attributes of those items?
Good question. We can calculate, so interestingly, I think I need more weeks on this. What do you think? Should I go another week on DCMs? I got lots of DCM stuff to talk about. On that note, I don't know, I'll think about that. But we got 30 minutes. I'll ask your opinion in 30 minutes. But to pick which item, let's think about it in unidimensional IRT world real quick. If this were what we were doing, how would you pick good items? What would you use?
Based on some kind of estimation of ability I'm interested in?
Yeah. You would normally think of items as, well, there's two characteristics, right? We want to know how discriminating they are and where that discrimination is located, right? We usually use that item information to describe this, right? We look at an item information function. Turns out that item information function, do you remember where it comes from? Like how we derive it. Second derivative of the likelihood function, in this case the item itself, because we can take the log like. So it's the second derivative with respect to theta, and because there's only one parameter in unidimensional, it's not really. It's like Hessian's usually a bigger matrix, but yes, it's analogous. That uses calculus, right? We have to differentiate the item response function with respect to theta, but derivatives are only defined on smooth functions, right? So there's no Fisher information we can use to calculate this. Instead, we come up with other versions of it. We can calculate versions of discrimination. We could talk about, sometimes people talk about something called a Kullback-Leibler divergence. We can talk about how much the probability of mastery changes as a function of this item. So 2 different distributions and how much they overlap. There's other methods. One is called Shannon entropy as well. But long story short, so we can come up with an index for each item of how much it informs us, similar to what we do in IRT. It just uses different architecture mathematically, and we can use that to describe it. Then there's the other idea. Another really quick, and sorry I'm going overboard on this, but I really want to. I can. So therefore, I feel like I should address this question. Here, let me get to the LCD real quick. Sorry. If this is our LCDM, right, this is with an interaction. If we want to know, for instance, we could come up with classical versions of discrimination describing how well this item discriminates for attribute 1. or for attribute 2, right? We could think of what's the probability, marginal probability, someone with attribute 1 answers it correctly versus incorrect, right? Only attribute 1. So you've got two master. You've got master. What's their probability? Non-master. What's theirs? We can look at odds ratios. We could look at classical discrimination, where one minus the other might be. There are ways of quantifying the impact of items. It's just with the interaction present, it's like impact in which dimension. Because you've got to remember that this item, if it measures 2 dimensions, it may not measure them equally well. So the question is, which one is where do you want to add it? How good of it does it turn out to be? It depends on which dimension you're looking at. It depends on what it does in the assessment. I don't know if I answered your question.
Yes. Yeah.
Hope that helps a little bit. How about everybody else? Other questions? Okay. Subsume models, we already talked about that. All right. You want to see how this is latent class model? Let's do that. All right. I made this for a job talk a long time ago too. Sorry, some of you are making job talk slides. I'm talking about my own version of it here, right? So, if this were not a DCM, if this was straight, let's imagine we take one idea from DCM, which is how many classes we have, how many unique profiles of people we have. In our 4 attribute example, we know there's 16. Right? So if I told you, go fit a model with 16 groups, and you didn't know DCMs, you might go to a latent class model, right? There's 16 different classes. And in here, this picture on the right has 16 classes. Now I've superimposed which attribute profiles they're supposed to be onto it. And here are our items. And each one of these is a probability that's based on that notation I used last week, that pi, representing the probability that someone in this class answers that item correctly. Right? I think I called them class-specific item difficulties, in the sense that in the classical item difficulty sense, the item p-value, proportion correct, right? How are we doing? Is the setup okay? Okay. That sounds like a reasonable idea. However, we know that there's nothing here that'll stop the class orders from being permuted, right? There's no guarantee when we estimate this model that class 1 really is somebody who's low performing on all attributes. So the labels are meaningless. And not only that, this first item, if it was addition and subtraction, and those are our first 2 attributes, we could look at these parameters and think, wait a minute, look at this first person. They don't know addition, they don't know subtraction. And this people in the second group, they don't know addition, they don't know subtraction. Why do we have separate parameters for them? Right? Furthermore, look, groups 1, 2, 3, and 4, all of them don't know addition, don't know subtraction. So really, if this is truly measuring that, we should see all 4 of these parameters being equal to each other. Really, we could replace it with 1. So what the DCM does is it puts a sets of constraints on the latent class model, where these are the items, 2 plus 3 minus 1, 4 divided by 2, 3 times the quantity, 4 minus 2. Sorry, this is in white. It's terrible contrast. I should have made it black to stick out. Another thing about making job talks or other presentations, high contrast. High contrast, always. Right? Visual. Okay. 2 plus 3 minus 1, everybody in the blue should have the same parameter. And that's what happens in the LCDM. Right? They get the intercept. People in the green should get the same probability. Well, what's that? 0 for the addition, 1 for subtraction. So they get the intercept plus the main effects of subtraction right there. Then here, this third group, they know addition but not subtraction. Same thing. They're all equated. And the fourth group there. So what the LCDM is doing, what the DCMs are doing, are putting cross-class constraints on our measurement model. Right? So this is one probability, one probability, one probability, one probability. We're looking at it that way. We went from, if this were a latent class model, 16 parameters for the first item that were unordered to 4 parameters for the second item. Right? That's what it's doing. Now, there's another set of constraints. Because these 4 parameters, there's nothing from stopping the latent class model software from saying this probability is higher than that, or it trying to flip the label of all these 4 as well. So we actually have to build in one more constraint to build this and that is that what our paper, Bob Mine and John Wilsey's paper did was basically say anybody who's mastered more attributes has a higher, equal to or higher probability of correct response. Meaning this green should have a higher probability than blue. This yellow should have a higher probability than blue. We don't know about green versus yellow because they both have one mastered attribute. We're not sure which one should go where. But the red, because there's two mastered attributes, should have a higher probability than both yellow and green. And because we know the green and yellow are bigger than blue, it implied that the red is higher than blue. We call this the monotonicity constraints, monotonicity. Meaning as number of attributes increases, that probability increases as well. So that's this part right here. So basically, there's our 4 sets of probabilities. I showed you the rows. Set 1 has 0 mastered attributes. Sets 2 and 3 have 1 mastered attribute, and set 4 has 2 mastered attributes. So we know that set 1 has to be less than or equal to either set 2 or set 3, and that set 4 has to be greater than or equal to set 2 and set 3. So how do we enforce that logistically? Take a look at these parameters here, right? Sometimes in my book we call these the kernel of the logit function because it's in the exponent. I don't know if that's the right term, but we like calling it that. We could show that for this to be true in probability, it needs to hold to be true on these parameters here. Right? And so how do we do that? Let's take a look. All right, so for set number 1 versus set number 2, we can show that probabilities are monotonically increasing if the response function, here's the intercept plus the main effective attribute 2, that has to be bigger than just the intercept. All right, that is this group, rows 5, 6, 7, and 8 versus rows 1, 2, 3, and 4. All right? So if we do that, we rearrange some math, we subtract the intercept from both sides, it means that main effect has to be bigger than 0. Right? Also, for set number 2 being less than or equal to set number 3, right? This one right here, this is for attribute 2. We have the similar function for attribute 1, right? Intercept plus attribute 1 has to be greater than just intercept alone, which leaves us thinking that attribute 1 also has to be greater than 0. So in fact, you can show for all main effects, the monotonicity constraints impose the main effects be strictly greater than or equal to 0. Right? So we have a lower bound to main effects. Bear with me? I know it's hour 3 at the end of the class, and I'm dropping monotonicity bombs on you. Who's the chump now, right? That's this guy. So, yeah. But, that being said, for the more complicated one, right, we've got the model where both attributes are, the kernel where both attributes are mastered, right? So this part right here, main effect, or intercept, main effective attribute 1, main effective attribute 2, two-way interaction, has to be bigger than the case where one attribute is mastered, which implies here that the two-way interaction has to be greater than or equal to -1 times the main effective attribute 1. So we could also do this again and again and again, right? This is attribute 1, and this is attribute 3 versus 4. Long story short, here are our monotonicity constraints. Both main effects have to be bigger than or equal to 0, and the two-way interaction has to be greater than or equal to -1 times the minimum of one of the main effects. And that thing right there, this set of constraints makes estimation of this model the biggest pain that we've faced in class yet. That's tough because this two-way interaction constraint depends on the magnitude of the main effects, right? If these flip, like if you think about what the computer's doing estimation-wise, right? It's trying to figure out where a likelihood shifts, and if you put a constraint on it, it can't go that direction, right? So it changes the surface a bit. This change is really difficult to describe because that region it gets into depends on the boundary or depends on the value of the main effects, both main effects, because it takes -1 times the minimum of both. That's an estimation problem that took me, I'm still working head over heels. It's still difficult to work head over heels. I'm still fighting with it after years and years and years. So the LCDM needs monotonicity constraints. What do you think? How we doing? I feel like I lost you all.
Can you go back, please, to the table with colors? Because yes, that one. So in the case alpha, those numbers within brackets
Yes.
represents people who are like masters.
That's right. This is the profile of attribute mastery. Yes.
Great. Now, for example, row 12, that pattern has 3
Yes.
domains, but it is yellow.
Because that monotonicity only applies to the measured attributes of the item. So the Q matrix, sorry I didn't fully explain that. That's my mistake. Forgot that part. Yeah. So for this first item, the only relevant entries in this bracket are the first 2.
Yes.
Right.
That's it. Okay, great. Thank you.
And similarly, like look at this last item. Look at the pattern there, right? That pattern, it requires, what is it? Subtraction multiplication. So it requires the second and the fourth. So now, if you look at the second, 2 and 4 here, what is it? No, is it 2 and 3? Excuse me, 2 and 3. 2 and 3, 0, 0, 0, 0, 0, 0, 0, 0, right? Then this ugly looking color here, 0, 1, 0, 1, 0, 1, 0, 1, and so forth, right?
Yeah.
Does that help?
Now it makes sense. Yeah.
Okay.
Thank you.
You're welcome. All right. 15 minutes left. Where are we at? How are you mentally, apart from exhausted? Anybody exhausted? Thanks, Lexi. I admire Lexi's honesty.
Yeah. Not gonna lie, my brain is kind of hurting on the
Monotonicity.
yes, the straights.
Yeah, and I'm throwing it at you.
Solve them to, I think it's just, yeah. I'll have to look at it again.
It's a lot. Yeah.
Yeah, I'm trying to create like an analogy for that.
Yeah.
And so if you go to the slide that's showing you constraints with the LCDM,
Where's that? In the right here? Which slide are you looking at again?
this one?
That one.
Yes, that one. So the last bullet point there. So can we imagine those like buckets? And you have 3 buckets, and you're filling the first bucket, the second bucket, but then the third bucket is the accumulation of the first 2 buckets, right? And so the estimation problem comes when you have overflow of the third bucket.
Kind of.
Okay. And that's why you have us like.
It may be a good way. I don't know if that's the right way to describe it or not. It might be okay. It may fit for you. I don't know that I can visualize it the way you are. That doesn't mean it's not inaccurate. So.
Fair, yeah. I'm just trying to like, yeah, have an analogy to it in some sense.
So let me ask this first question. Is the math behind it okay? Is that what's causing the confusion? Because I can go over that a little bit better.
I don't know if it's the math. I mean, we just went through it, so
Okay.
it might need some time to sink in
Yeah.
to build a better analogy than
Well,
just plug
well,
it.
think of it this way. Here, let me try one more time. And if this is overly repetitive, let me pause here because I'm gonna run out of time. Do you want more of this next week? More DCMs, or do you want me to skip and do something else?
What's the other lecture?
I was going to do latent variable interactions in MERT, bifactor models, higher order models, which I can make the week after Thanksgiving break. I can spend more time with DCMs. I can talk about structure and how we estimate them next week. Would that be?
I would like to hear about this.
It looks like people are interested in this.
Yeah.
And honestly, if I teach this class again, most of you are going to be gone by the time I do it. So, because I teach so infrequently. So, would you, I mean, I'm happy to do that. I don't want to like make you do it. I know, of course, then again, it's not a democracy. But I'm giving your advice. I don't want to take a vote, but how many of you, actually, yeah, I will take a vote. Forget it. I don't want to, but I'm going to. How many would be supportive of DCMs again next week? How many would like the other topics? It's okay, raise your hands. I see most hands for DCMs. If you're one that wants the other topics, after Thanksgiving break, I'll put some in there. We got 2 weeks there to talk about things, but actually next week I'll talk about for DCMs is how to estimate them in the structural model, but we'll get more experience with it as we go through it. Thank you. I'm so sorry that, yeah, I'll do that. All right, so then let me do this. Let me wrap up this week. I have some comments, but I'm going to make them off of the YouTube. So everybody on YouTube, you won't know what I'm going to say to my group here. Okay, so goodbye, YouTube.